Hello, Stats class. Here's lesson 14.1c, and I want to say this is a special lesson, and the reason is it's the last one. It's the last new lesson of the year. So we are continuing to do multiple regression, which means we are using 2 explanatory variables. It can be done with more, but we're going to stick with 2. And we're still going to have 1 quantitative one and 1 categorical. And we're still going to predict a quantitative response variable using those variables. What's different about 14.1c is in A and B we were working with parallel lines, and now we're going to do non-parallel lines. This non-parallel lines thing is officially called interaction, and I should have maybe put that as part of the title. Interaction between the variables. And so basically today we're talking about what if the lines aren't parallel. It's just one step beyond what we did before, not much more. And then if you want to learn more about this, take another stats class in college and they will teach you more. In fact, in graduate school, I spent a whole quarter doing a whole class on multiple regression and all of its different forms. You're just getting the basics. So that's okay. So what if the lines aren't parallel? That means you've got 2 different slopes that we have to include somehow in our model. And that makes the calculations a bit harder, but not actually a whole lot harder. So I'm going to again draw a scatter plot and tell you the story as I'm drawing it. So this data comes from SAT information and basically taking different high schools and finding the mean math SAT score for the whole school. And obviously some are higher and some are lower. And then also looking at the percent of students at that school who take the SAT. So now, this may or may not surprise you, I don't know, but the schools that have fewer people taking the SAT tend to have a higher mean, and then the schools who have almost everybody taking the SAT tend to have a lower mean because basically everybody's included in that, but it's not a straight line. It's kind of a weird looking graph, and I'm going to do this. And I'm going to say there's this piece that goes down like this, and then it kind of kinks and starts going like that. So there are 2 ways to deal with data that looks like this. We've actually seen one way already. It looks like it's curved. We could try to straighten it. That is the old way that we did in Chapter 12, specifically Chapter 12, Part 2, which we did first. But anyway, the old way is to straighten the curve. And that sometimes works. This particular data doesn't work that well with straightening the curve because it actually isn't a curve. I don't know if I drew this well enough for you to see it, but it actually has a line that goes like this, and then it has another line that goes like that, and that's interesting. So our new method that we're going to learn today is to separate the groups. This should remind you of what we did in the very beginning of the year with if you had a bimodal graph, you tried to separate them into 2 pieces. So like if you had 2 humps or peaks, you try to figure out why, and then you looked at this group and this group separately. And I'm not going to draw that because that's not what we're doing right now, but this is another situation like that where we have a group that follows this trend and a separate group that follows this trend. And if I could just figure out what those groups are about, then I could fit 2 lines instead of 1, which isn't such a bad thing. And then with my multiple regression skills, I could make it all into one big equation, which is what we're going to do today. So here is what happened. The researchers who were looking at this actually figured out why there are 2 groups. And what happened was this upper line is the East Coast schools. And this lower line are the West Coast schools. No, that doesn't mean that West Coast people are stupid or anything like that. The West Coast, we tend to take the SAT. Like, we tend to give the SAT to every student at our schools, and because of that, the mean scores tend to be low. East Coast schools, they are more likely to do the ACT. And so in a school where everybody takes the ACT, who does both? Who are those students who take both the SAT and the ACT when it's not common to do that? Those are the smarter students. Generally, the strongest students take both on both coasts. So if I did a graph just like this for the ACT, then West Coast would be over here and East Coast would be over there because the ACT is more common on the East Coast. So their students, the very few, small percent of students who do that, tend to be higher scores because they're the stronger students. So there's no mystery to it. It's kind of an interesting thing that happens, and it doesn't mean East Coast is better. It means that they are more likely to take some other test. So there's two ways that we could divide these into groups. We could find this dividing point and say maybe that's about 40%, and if you're under 40%, you go into this group, and if you're over 40%, you go into that group. That's not what we're going to do because they figured out the trend. We're going to use East Coast and West Coast. So what we're going to do is we're going to take our two groups, and we're going to say if it's an East Coast school, remember these are whole schools, not individual scores, then we're going to call it 1, and if it's West, we're going to call it 2, or 0, usually it's 0 and 1. Remember, this is called an indicator variable. And we're going to call that x2, like we did before. And x1 is going to be the mean math score. No, it isn't. This is y. Y is the mean math score. x1 is the percent taking the SAT. So we still have x1 and x2, but there's something else that's kind of fun. So I'm going to show you the new form of the equation. It looks like this. Remember, we are using y hat to estimate the mean math score overall, which is called uy. So I'm going to give this to you in parameter form, and then the statistic is called y hat. So this is the mean math SAT score, the average for all the schools, right? And we're going to have, kind of like what we had before, we're going to have beta 0 plus beta 1 x1 plus beta 2 x2. And so far it looks like what we've done, right? There's another piece that we're going to add on here. But before we go to that other piece, I'm going to point out that x1 is the percent taking the SAT, which is a quantitative predictor or explanatory variable. X2, as I said up there, is the indicator that says whether you're East Coast or West Coast. I don't know about the middle, and we're not going to worry about them right now. East or West. So we already talked about that. And then there's another piece that we're going to add on that indicates the difference between the slopes of the two lines. And I'm going to just write it first and then explain why this makes sense. So beta 0, beta 1, beta 2, the next one logically should be called beta 3. But it doesn't go with x3 because I don't have another variable. What I have is an interaction between x1 and x2. In other words, I have the slope changing depending on which group we're in. The way that happens mathematically is by doing x1 times x2 as my third variable. Now that's very interesting, isn't it? This right here is called the interaction between the two variables. Now we saw something like that with the mazes. So I'm going to take a tiny break from writing, and I'm going to tell you that with the mazes, we saw that we might have a width of the maze as one of our explanatory variables. If I was willing to let this also be quantitative, which by the way I forgot to label it as categorical. If I was willing to let this piece be quantitative, then I would have two quantitative variables, and possibly the area of the maze also would be my interaction between two quantitative variables. We are not going there. We are not going to do that complication this year because we're almost out of time this year. But I wanted to let you know that that could happen, that we would have length and width and area as three separate predictors in our equation. But what we're doing today is quantitative and categorical, and what happens when you multiply those together? Well, let's take a look at that. Let's put a big box around this because it's important. And then I'm going to take this equation and split it up into its two separate linear equations, like we did with the other ones that didn't have this piece. So we're going to look at the west coast here versus the east coast and see what happens to the equation, and that will help us make sense of what this means, and that's why we're doing it. So west coast means that x2 is 0. If x2 is 0, this piece is 0, and this piece is 0. They're gone. We just have this first piece only. This is a simpler situation than the other one. So mu y would equal beta 0 plus beta 1 x1. And as you know, this is the y-intercept, and this is the slope. However, it's not just any y-intercept and slope because there's two graphs, and they have different x-intercepts and different slopes, right? This is the y-intercept for the west, and the slope for the west, which is different than the y-intercept and slope for the east. Let's start color coding this. So I'm going to make the y-intercept for the west be pink. And the y-intercept for the west, I could find it on the graph by just making this line keep going. In fact, I'd rather make it solid than dotted because I don't want it to look like more dots for my scatter plot. But this height right here is beta 0. Or if we were looking at the sample data, it would be B0, right? That's the y-intercept for the west coast. I can see that the east coast y-intercept is way higher. We'll get to that in a minute. Okay, so then let's look at slope. Slope, we did yellow on the other lesson, I think, so I'll do yellow again. The slope for the west coast specifically is how much it goes down every time it goes 1 unit higher. So every extra percent of students taking the SAT would cause that slope to decrease by a certain amount. Beta 1 is definitely a negative number. Don't know what it is yet, but we'll get there. Okay? That's what happens if we're on the west coast. What if we're on the east coast? We would have x2 equals 1. So that means this piece would now have a 1, and this piece would have a 1, and we get an equation that has all four pieces in it. So mu y equals, we're going to just write it all out, beta 0 plus beta 1 x1 plus beta 2, x2 is 1, so I don't have to write that, it's times 1, right, plus beta 3 x1, I don't know what it is, so let's write it down. X2 is 1, so I'm just plugging in 1 into these two places and simplifying. That's what I've got. That's an ugly looking equation. It is a linear equation though. It has two pieces that are whole numbers, or well, maybe decimals, but they're numbers. So I could add these two pieces together and combine like terms just a little bit and get beta 0 plus beta 2. And then I could also add these two like terms and get beta 1 plus beta 3 x1. That's looking a little bit better because this whole piece is now the y-intercept. This is the y-intercept for the East Coast students. What does it look like on the graph? Well, we have beta 0, which we already labeled. We have beta 2, which is the extra piece added on for the y-intercept of the East Coast schools. That's this piece right here. When you add them together, you get the y-intercept for the East Coast. So beta 0 and beta 2 added together make the y-intercept for the East Coast. Okay, then let's look at this piece. Beta 1 plus beta 3. That's the slope for the East Coast. Okay, so beta 1, I'm using yellow for that, and I don't have another color handy, so I'm just going to not color code beta 3, but that's okay. Beta 1 plus beta 3 is this slope right here. That is how far down the East Coast goes every time you add a percent. This piece right here is beta 1 plus beta 3. Is that piece. Okay? So I can tell that it's negative. I can tell that it's more negative than just beta 1, which means beta 1 and beta 3 would both be negative numbers in the computer output. to show that the slope is negative, and then when you change the slope for East Coast, it becomes even more negative. These would both be negative numbers. These would both be positive numbers in this example. So this, to me, makes it make sense. This weird thing is hard to understand unless you think about what happens if you plug in 0 and what happens if you plug in 1. Then it starts to make sense, because then we just have simple y-intercept for west, slope for west, and then we have slightly more complicated y-intercept for east is adding these two together, and slope for east is adding these two together, the two that have x1 on them. So let's do this with some numbers next. So you plug it in the computer. You don't have to do that because the book will do that for you, or I will do that for you. You read the computer output. The computer output is set up the same exact way as all the other computer outputs we've done for linear regression, where it has a predictor, and then it has a coefficient, and then it has SE and T and P, and we don't need to worry about that right now. But the predictor, okay, let's think about this. The first one's always the y-intercept, right? It's going to say constant. And then it will list the three things that are going into three things, not two, the three pieces for beta 1, beta 2, and beta 3. So what we've got is x1 is the percent who take the SAT. That would be the name of x1, or what they coded it for. We have x2, which is our indicator variable, and they called it east-west. And then we have our interaction variable, which is x1 times x2, and they coded it like that as a times, like the star means times in computer programming. So this is our interaction between the variables. That interaction just means that the slope depends on which group you're in. So then here are the coefficients. I'm just going to copy them from the computer output that I already looked up. And all of those would go into making an equation. So now all of this stuff over here would be for inference, which we're not going to do inference with this type. With the interaction, I don't want to add one more lesson. So this is for inference. Technically, it's the individual t-tests that we talked about in 14.1b. There might be a little bit of that in your homework, but I don't think that it will be on the quiz. I'll decide that for sure by Thursday. So the individual t-tests for testing whether each of these is important, that information is there. You already know how to interpret that, but right now I want to take this and make my equation. And remember that this is the parameters. This is based on the population. Let's do the one that's from the sample because that's what these numbers are. So these are estimates of the betas, and they are called B0, B1, B2, and B3. And we put them all together to make a y-hat equation, which is y-hat is 528.65. That's my y-intercept for the first group. Here's my negative. Remember, we already talked about the slope is negative. X1. We have plus 69.65 x2 minus 2.432 x1 times x2. There you go. What does this mean? Well, we can interpret these numbers, and that's probably a good idea. This right here is the y-intercept for the west. So the west has a y-intercept of 528.65. What does that mean? That means in schools where nobody takes the SAT, oh, that doesn't make sense. But if there were schools where nobody takes the SAT, this is the predicted mean score on math. But it really doesn't make sense in that situation. And the slope for west is negative 0.32. And again, we could interpret that. I'm not going to write it down, but you could think about if you add for every additional percent of people taking the SAT, the mean score goes down about 0.32. It doesn't go down a whole lot. Not a very steep negative slope. But that's for the west. For the east, the y-intercept is two pieces added together. So remember, you add the 0 and the 2, the two even ones, added together make the y-intercept for the east, which is 528.65 plus 59.65. If you, interesting, there those 6 5s. I did copy that, right? Okay. If you add those together, you get 598.23, which is the predicted average score for an East Coast school that has nobody taking the test. Again, doesn't make much sense, but that's okay. Slope is you have to add together these two that have the x1 on them. So watch for that x1 to find the slope. Slope would be negative 0.32 plus negative 2.432. If you add those together, you get negative 2.7 something. It's not perfect. 752, and that's the predicted decrease in mean math score for each additional percent of taking the SAT for the East Coast schools. So you could find these, you could use them to write separate equations for the East Coast and West Coast like we did up above. You could use them to plug in numbers and predict the mean math score for a school based on which coast it's on and what its percent is of people taking the SAT. You could do all the same stuff with this that we've done before, but this is the equation. And the most important thing you need to know is how to get this equation from here and how to change it into two separate equations. So how to find the y-intercept for west and the y-intercept for east, and how the slope for west and the slope for east. That's mainly what we're doing today. And we're not going to get the details. We will get the details later. Or actually, you will get the details later if you take more stats in college, which I hope you do. So that is it for today. We will do review on Thursday, followed by a quiz on this. And the only other thing I need to say is finish your project. Rough drafts due Thursday, final drafts due next Monday. Get it done. Thanks. Bye.